Okay, so the first thing I was going to show you is like the problems that I just posted on Canvas. Maybe I should go to that first. Like in a sense, like the problems are not that there's each problem is short. It's just going through the entire paragraph just like explaining the context, which would make it look that long. But if you kind of like start reading them, you'll see, oh, it's very little that I'm asking you to do. It's just like kind of like putting a lot of background to under so that it doesn't feel like a too much of like an artificial problem of why did I choose this one over the other. I mean, so far we haven't done too much. Like we're starting to get close to finally learn homology. And once you know what homology is, then you can actually use that to do a lot of computation. So that's kind of like the key ingredient of the course, these homology groups or homology vector spaces are. So in the meantime, I just put like some like stuff, which is interesting, just like for just having some general knowledge and also just for some experimentation. So like I put like a deadline. It's not kind of like a deadline that I will enforce too much. I'm more interested in you taking your time to, like working on the problems. And also if you have any questions, you can always ask me either in person or via email. Um, but yeah, it's more like for you to kind of like just think through these things. So like the first one, okay, it's again very more like to see whether like what sort of like intuitive sense of topology you have. So like if you have like those letters in the alphabet. So again, like if you think about them as being made out of rubber, the idea is that the shapes are kind of considered the same from a topology's perspective. If you can kind of deform one into the other. But as I explained there, like the rules of the game there are certain things that they don't allow you to do. So, for example, I have a cable here. So, for example, if you take like a cable, like a line segment, if you were to glue the endpoints as we talked about, that would give you a circle. And you do want to think of those as being very different things. So you definitely want to think about of an interval as being different from a circle. So that like gluing in that sense can give you like a shape that's different. But if you had like again, like this won't come out that nicely, but if you have like a circle, that can be deformed a little bit, and you could have like shapes of this form. I mean, this doesn't almost looks like the letter B. It's not quite the letter B, but like you could have like or like more like the letter O, right? Like so, a circle would be kind of like the same as the letter O because that can like kind of be deformed. So basically, again, it's it's more qualitative but it's more for you to think about like oh, if I thought of them as being made out of rubber, without like cutting them or gluing them, which ones can be deformed to the other. So it's kind of like a type of classification problem. But I think you're free to ask me if you just want to check. The other one is more like this, just to introduce the definition of a distance. So that's going to be useful later on. Like the distance that is the distance on our end, right? Like the distance between 2 points on our end, which is just like the Pythagoras theorem, right? Like it's also called the Euclidean distance. But there's like a very big generalization of what it means to have like a distance that's called like a distance function. And so there's kind of like going through like the definition of what it means to have a distance function. And I give you an example which like is convenient when the space or the set that you start with is like a finite set. So you could have like a finite set like which you can think of as an alphabet. So once you have an alphabet, you can make words with it, right? So for example, like in biology, like for genetics, like the alphabet could be for like the nucleotides. So like it's like a four-letter alphabet, but like in computer science, it's more common to have like the alphabet just being strings made out of like zeros and ones, right? So you can create words and like you can define a distance between words. Um, Here, like, and again, I kind of go through like the explanation of how it's defined, but basically what you do is kind of like you count the number of like letters, like the number of entries where the symbols in the words are different. So for example, if you look at those two, well, words in quotes because it's not that it has any particular meaning, right? Like there's no semantics here. It's only syntax, like just like string characters concatenated. But if you look at these one, they differ in the third spot because this one has a G and this one has a C. And also they differ in the fourth spot because this one has a C and the other one has a G. So they're I mean this sometimes called like the hanging distance, they're hanging distance in these cases too. So again, this will once we kind of like go into more like discrete, like for applications or discrete settings, that is actually like a useful distance function. So like the problem is just to check that it does satisfy the properties of a distance, which I spelled out a bit later. But as I was telling you, it really is more not there's not much to prove. It's just going reading through the paragraph to say, oh, this is like the definition, and this is why I'm doing this example. And then the third one, again, is just for you to check these things about, oh, so you have like a dot product between vectors, which you can generalize to a dot product between functions. Again, this is kind of the fancy notation for the dot product of functions, which is typically just referred to as an inner product. So you don't call it a dot product anymore. You just call it like an inner product. So here I'm just saying, okay, let's just check, which we kind of did a little bit already in class. So part of it is probably on the notes if you go through them. But what I was saying is that, let's just check that if you have an even function that's perpendicular or orthogonal to an odd function. And also that you can kind of like extend a lot of the ideas of linear algebra. So for example, in linear algebra, you can talk about projecting a vector onto a space. So you can't project a function onto a space, and that's kind of like, I'm giving you like an example here, like where like what these I'm calling it P for projection because that's literally what it's going to do. It takes a random function and even makes it it turns it into an even function, which is kind of like this trick that I mentioned. If you just add to a function f and negative x, that automatically becomes even and divide it by two. So it's kind of like a projection where you take a function and project it into its even version. So like, there are many analogies that kind of like of things that you learn in your algebra that literally can be done in this case. So in a sense, you should think about this as similar to a matrix. It's just that it has like infinite size in some sense. But then you can ask for what's the null space of that matrix or what's the image of that space of that matrix and so on. So it's kind of like, again, just to check some of these things that I was mentioning, this is like a very fun one. The transpose of the derivative is one of my favorite examples. So again, you just end up using integration by parts, and it gets for you to check that the transpose of the derivative is minus the derivative. And that's kind of like interesting because I make a remark here. If you use complex numbers, which we won't, so basically, once you have complex numbers around, you also are supposed to take the conjugate of a complex number. Basically, the conjugate of a complex number, I don't know how much you remember about this from like Calc 2 or like, I don't know how much you remember this from Calc 2 or linear algebra, but I think now you do complex numbers on linear algebra. But a complex number was something like x plus iy, right? And its conjugate, it just flips the imaginary part. So it's just x minus iy. Well, anyways, so you can multiply the derivative by the number I, and the way the conjugate is supposed this is called the adjoint. And so you conjugate that I, so it becomes negative I, and you take the transpose of the matrix. Well, matrix equals, right? It's infinite dimensional. But then because of the previous part, like the transpose of the derivative is just minus the derivative, so minus times minus gives you the same. So what you end up finding is that this is that this adjoint, which is kind of like a transpose, when you multiply the derivative by I, that gives you the same. So that's the analog of a symmetric matrix when you have complex numbers around, and that's useful because, for example, that is like how like in quantum mechanics, you represent like the position, like the momentum of a particle. So you represent it by like a derivative, like what they call like an observable, which is just a fancy way of saying a self-adjoint. Self-adjoint is kind of like the version of symmetric. So it's kind of like self-adjoint operator. That's what they call that. But it's kind of like similar to symmetric matrices because a symmetric matrix has real eigenvalues. So like these observables have like real eigenvalues, and then the eigenvalues of that corresponds to like the possible values that you can of the position of the particle that can be measured. So again, like so there's some technicalities, but if you ignore those, they kind of work in the same way. And the last two are like this thing that we were talking about the other day about the curl and the divergence, the gradient, and all this stuff. So just for you to check some of those things that I was mentioning, that these identities, like for example, the curl, the gradient vanishes, or the divergence of the curl vanishes. So for you to work it out, it's like kind of like a brute force calculation, but it's still like a valuable thing to at least do once in your life. So and because I will use that later on, and again, like this assignment is 85% just remarks. So if what I was mentioning here is, like, for example, if you look at Maxwell's equations in vacuum, in the electrostatic case, it just means that the electric and the magnetic fields do not depend over time. So, like, if you just look at the Maxwell's equations in vacuum, where there's no matter present in electrostatic case, then there's one of the four equations says that the curl of the electric field is zero. And if you're working on R3, that tells you that the electric field is the gradient of a function. The physicist just called minus the function, the electric potential. So that's how you get that the electric field is minus the gradient of the electric potential. And for the case of magnetism, there's something similar because one of Maxwell's equations is that the magnetic fields are solenoidal or like the divergence free. And because of like all this stuff, you can find a vector whose curl gives you the magnetic field, and that is called the magnetic potential. And then what the last problem says is that, oh, this very nice thing that happens on R3, which is what actually does not happen anymore if your universe were like three-dimensional but of a different shape. So it's kind of like just to run down this example that I was telling you about with the wraps and the cheese. So like right, like if you have, as I was saying earlier, if you have a segment, one way to think of a circle is it's literally a line segment where you just connect the endpoints. So you can kind of like do something similar here, where if you take a square, a piece of paper, and you kind of like glue together the two blue sides, and you glue together the two green sides, you get a torus. What we call torus in mathematics is just a donut. So in fact, that you can kind of more or less do with a piece of paper if you just try it out. Like you see, again, like you get a cylinder very easily when you glue two of the two sides together, and then you just have to imagine, like, again, stretching out like the cylinder to connect it to a donut. So, and then what I was saying in class is that there's kind of like a 3D version that you can do there, where like if you imagine like living in a box room, where you have like where as I walk towards the door, like if I reappear from that opposite side, and if I go through the floor, I reappear from the ceiling, and if I go through the board, I reappear from the other side. That is called like a torus, like a three-dimensional torus, and that is generally a different space than like ordinary space because that doesn't have that property. Oh yes, sorry.
Is this like the sphere with like a hole inside?
If it gives you the same as a sphere with a hole inside, you mean?
Yeah, it's the same.
Sphere?
If you move it, you get like a root to the blue, you get like energy.
I have to think about it. Let me think about it because at the top of my mind. Yeah, I don't know. Like actually, you're saying, well, you mean like a ball?
Sorry, it'd be like a torus, it'd be like a hollow.
Right. But no, I'm thinking like I mean because if the thing is like when you said sphere and then you were thinking about like a ball, right? Like because like this is going to be three-dimensional because I'm including the room itself, right? Like the inside of the room. So
It's not like let's be like a torus with like some volume.
oh, it is not a solid torus. I see what you're saying. It's not just a donut with the inside included. That is not like no, because
There's like a hole inside.
well, it actually will have three holes. Like in a sense, it will have like well, like it depends what you mean by hole. We will be more precise. Like part of the point of this course is kind of like to be right.
Inside it's like hollow.
Yeah, it's kind of like part of the point of the course will be to define what you mean by hole in a sense. What I meant to say is that I think I had mentioned this on the first day of class. Kind of one way that one of the interesting things, like, you kind of like see this circle, right, like wrapped around the donut. If the donut is hollow, right, if there's no inside to the donut, this one cannot be contracted, cannot be shrunk to a point by staying within the donut. Same with this other, like, longer circle that you see here. So in the case of the two torus, like, they're kind of two curves, which are kind of like, in a sense, independent of one another, which cannot be contracted to the point. In the case of this version, like 3D version of the torus, there's something similar that happens, but now there are three of those, like, which are kind of like distinct. Um, what I was going to say, uh, is that this space, well, I couldn't, in this picture, I should have drawn I should also have colored the opposite faces. I said, otherwise, like, it looks messy. So, like, it really is like the cube, you take a cube, and you kind of glue together opposite, like, the faces that are opposite to one another. But my point is that that's generally like a three-dimensional space that is not like regular R3, because again, regular R3 doesn't have this almost like teleportation property in a sense, like, where, like, if you go to one of the edges, like, you reappear from the other one. It doesn't look weird if you live in that universe in the same way. If it doesn't look weird when you're in the circle, that you just can't keep walking on a circle forever, right? But if you look at it, if you think of the circle as kind of like a segment with, oh, once you get to this endpoint, oh, you reappear here, right? Which kind of like looks like magical, like, I mean, there's actually somewhat related to this wormholes. I know this other stuff, like, your relativity, but so it's not that there's something fishy going on. You're not teleporting yourself. It's just like, if you look at it from a certain perspective, it does look like that, but from the outside, on the inside, it doesn't look like anything odd is happening. But anyways, what I'm saying is that here it's very straightforward to write down a vector field whose curl vanishes. So the curl vanishes, but it's not the gradient of any function. So in fact, if you wrote Maxwell's equations, you can write Maxwell's equations in this universe. And in that case, it would not be um, in that case, where do I have Maxwell's equations written? Yeah. In that case, you could still have like this version that the curl of the electric field is zero, but that wouldn't allow you to conclude that there's an electric potential. Like, that's kind of like the idea. So they just behave like, the fields would behave differently. So kind of like the electric fields and the magnetic fields are actually sensitive to the geometry of the space where they are located. Um, so certain things that, when you're analyzing, like, the electric fields and magnetic fields in a regular standard electromagnetism class, you are using a lot of, like, in on the background, the fact that you're working on R3. Like, if you were working in more complicated spaces, um, then not everything is necessarily the same. You might think, oh, I'm not interested in working in more complicated spaces. But another way to think about a more complicated space is just, oh, you have a field with a singularity. So it's just like maybe the electric field becomes like infinite, undefined at some regions in space. And in a sense, you kind of, that shouldn't be considered as part of the region where the field is being defined. So that's kind of like a more, maybe better way to think about what's happening. That you can still maybe think that you're an R3, but the field is not defined everywhere. And so that's where, like, the shapes can become more interesting. See, but as I was saying, like, most of these problems, it's mostly reading through them, but like, in terms of like what I'm asking you to work on to do, the execution of like the calculation is not too long. It's just like that I'm giving a lot of background, so that if it feels like kind of more clear why I'm putting this instead of another problem. But you can take a look at them, and as I was saying, like, if you have any questions, just can ask me about it. And like, the deadline that I put is kind of like more like a fake deadline, like, just do it on your own time. But I mean, there should be plenty of time. You just see it through them. But maybe some of those, it's more like parsing out what I'm asking you to work on. That could be the most confusing thing. But once we have finished doing homology, we can do more like applied problems, where I still want to do kind of like these ranking problems where I give you some data, we will kind of like create like a ranking, kind of like a Netflix type ranking for it. And it will involve like these ideas of geometries that you create, like associate a space to the data, and you see whether does it have holes, yes or no. and that plays a role on how it can be ranked or not. But anyways, I wanted to go through the problems because they are, I'm writing them so that they are parallel to what we're doing in the course. So it's not just like, oh, let me just put a problem because I have to write something down. It's just trying to kind of choose them strategically so that they're kind of like of in close connection to the course. Uh, okay, so to go back to what the situation that we were in uh, last time, and again, like this is kind of like the piece of information that we need in order to start doing like more interesting things. So we're kind of like almost there. Um, the situation that we had were like two matrices, right? Whose product was zero. Um, so like let me just do it like in the diagram, the way I had written the diagram from before. So you have two matrices A and B. Again, the matrix, like the first matrix, which we're calling B, it goes from RL into Rn, and the matrix A goes from Rn into Rm. Again, the way that this works with the matrix sizes is that it kind of gets flipped. So A is, for example, an M by N matrix, right? And B is, for example, an N by no, sorry, sorry, like this one is flipped. This one is N by N. It gets flipped, so N by N matrix. And the other one is, what am I doing? I feel like I'm doing something down here. Let me just double check. Ready, sorry. I want A to be N. Right, okay, okay, yeah. Yeah, because I have to, it will multiply a column vector of size N, so that's why it's N by N. Now that's fine. And then, oh, B was, oh, did I write this the correct way? So B was, I think last time I wrote it, because last time I wrote it A times B, and so A was N by N, and I want B to be N by L. Oh, no, no, that's fine. Oh my God, I'm doing it. Stupid matrix sizes. Sometimes you get confused. Right. So this is still. Oh yeah. It's like I see what I was getting confused because right. When you see this, these basic notations, like when it's not like from this perspective, it's not that these have to match. It's kind of like the outside ones have to match because if you write it like this, now it's fine. So it's like there was very two different ways in my head. Okay, so now this is fine. So you have like this situation. And the idea, the assumption was that this is kind of the zero matrix, right? So the zero matrix of size is M by L. So this is the assumption. Now, what I was saying is that because of this, once this happens, then the null space of there is an inclusion where the null space of the matrix A contains the column space of the matrix B. So let me write it down here. So what you end up getting. So the null space of A is larger in general than the column space of B, and I'll make this picture a bit more clear in a moment. But the important thing here is like, sometimes they could have the same size, But what is true in general is that the column space of B is always a subspace of the null space of A. Okay, and so you because of that, we are in a similar setup to, sorry, just to go back to the previous note so that you see that it's kind of like the same idea of what we were doing before. When was this? Like, I think I was, yeah. Well, even one class before, like lecture 4. Right. We are in this in this setup where you have a vector subspace of a larger space, right? You have a vector subspace of a larger space, so you can say that two vectors are related if their difference is in the smaller subspace. So I'll do exactly the same here. Let me just like make a kind of like enlarged version of the space in the middle because this is going to be the key one for all of this. So here I have Rn. And then just to make this picture a bit nicer, I have the null space of A. And this looks much better. Yeah. And here you have the column space of B. So again, I'm trying to draw them in a way that kind of like clear that column space is inside of the null space. So you want to say the two vectors in the null space, let me call them U1 and U2. So the equivalence relation is that if U1 is related to U2 if U1 minus U2 is in the column space of the matrix B. And again, here in this picture, here U1 and U2 are already in the null space of A to begin with. And that produces what we were calling the quotient, this quotient of the vector spaces. So this is a quotient vector space. I mean, the equivalence classes are this null of A divided by the column space. They're just a fancy way of referring to the equivalence classes that you get. So the equivalence classes. But okay, so this is why we talked about the orthogonal complement, because as what I was saying last time, or like maybe for the last 2 or 3 classes, is that there is a more concrete way to think about this, because this is just the orthogonal complement to the subspace, okay, to the column space. But you don't care about, again, let me try to, the problem with all of this is that just doing the right diagram. So essentially, you have here the column space. Sorry, you have here the null space of A. Let's say here's the column space of B. And then you have, the column space of B has kind of like an orthogonal complement, right? Which we can call like the orthogonal complement to the column space, right? By the rank nullity theorem, or when we were talking about the rank nullity theorem, we had said that the orthogonal complement to the column space is the null space of the transpose. It's kind of like a bit of like a word salad, but this is the null space of B transpose. Okay. Okay. So basically the idea is that the quotient corresponds to the orthogonal complement of the column space, but only the part that already lands inside the null space, because we're doing the equivalence relation only in the null space. So there's kind of like this overlap region. Actually, let me use red because that one I can write. So this region that I'm coloring in red is uh in the null space, but it's also in the orthogonal complement to the column space. So this overlap region corresponds to the intersection of the null space. Oh, so this is the symbol for intersection. I I think you said it in linear algebra, but I just mean like you just look at the vectors that are both in the null space of A and in the null space of the transpose. Okay. So this means like it is, this consists in the vectors that belongs to to both um subspaces. So these are just like the vectors W, or how am I calling this, like U? These are the vectors U in Rn, where it belongs to both subspaces. So where what it does it mean to belong to a null space that it's of the homogeneous system. So you have that A dot times U is a zero vector, and then V transpose times U is a zero vector. Okay, so what I'm saying is that is a more concrete. In fact, it will become even more concrete in a moment. But at a first glance, this represents the equivalence classes of the previous equivalence relation. So you can think of the equivalence classes, this quotient space that I have mentioned before is the same as this intersection. So the idea is that this null space of A divided by the column space of B is the same, can be represented as the intersection of those two things. Let me show you the picture. So, I mean, just to, again, to just recap, because this is a little bit abstract, it's probably the most abstract that we'll get in this class. Like after all of the, we just have to get the machinery in place and then we can just start doing, like, computations. But just to kind of like recap, the column space sits inside the null space. You create this equivalence relation that two vectors in a null space are related, either different size less in the column space. And all that I'm saying is that those equivalence classes can be represented in terms of the vectors that belong to this region, which is the intersection of the null space with the null space of the transpose, because the null space of the transpose is your orthogonal complement to the column space. Okay, so it's again, it's like a little bit of a word salad, but all that I'm saying is that at the end of the day, you can forget about this quotient, whatever that is. And I'm just saying that we're just looking for the null space of A intersected with the null space of the transpose of B. Yes,
Was it like saying that every vector in that intersection is like it represents a equivalence plot?
exactly, yes. And there's even, okay, and this is kind of the, again, the last abstract thing that I'll say, that there, or in fact, if you make it more concrete, there, you can think of this intersection as the null space of a single matrix. And this is called, I mean, I'll call it the Laplacian, because the Laplacian matrix, because it really would correspond. I don't know if you have seen the Laplacian like before. So the Laplacian, just like before I continue, like as a small remark, I'll put it. This will become one of the later, like one of. I'll add this to one of the assignment problems, but for like next round, not for like the one that I just posted. But if you have a function, if you have a function, the Laplacian, if like if you have a function f of x, y, z, the Laplacian, oh no, this is a gradient that okay, how did the people write the Laplacian? I think they write it with this upside down triangle. So the Laplacian is just the sum of second order partial derivatives of a function. Uh, this is like again, this is like a very important thing, because there's a thing called the Laplace equation. The Laplace equation is just that the Laplacian of a function is zero. So I don't know if you have heard, there are many different equations in like mathematical physics. One is like the heat equation, which just tells you how heat propagates. Another one is like wave equation, which tells you how wave propagates. And the other of the big three are the heat equation, the wave equation, and the Laplace equation. Those are kind of like the triforce of PDE. It's like PDE is partial differential equation. Basically because each of them represents like a different type of equation, which are called elliptic, hyperbolic, and parabolic. Um, so the Laplacian is like the one that's called elliptic. But anyways, like the point is that this is like a very important equation. It appears all the time in electromagnetism. Uh, if you put a set of zero, you put like the electric density, the electric charge density, that's called the Poisson equation, if I'm not mistaken. So it's kind of like usually you solve it because you have like it's kind of like you want to find the electric potential if you know the charge distribution rho. For that, you have to solve the Laplace equation. So it is one of the key equations of like mathematical physics. But the idea is, if you apply, again, like it's too much to go into right now of a detour, but there is a way to connect this to this construction we're doing with the curl, the divergence, and like the transpose of a matrix. So it is kind of like it does pop out from like what I'm saying right now. Like you can kind of find this Laplacian from what I'm saying if you kind of like do kind of like an infinite dimensional version, because this is kind of like um What is the Laplacian? Is the divergence of the gradient, if I'm not mistaken. You see, like it's kind of like an easy thing to check that would give you the Laplacian. And the idea is that the divergence is kind of like minus the transpose of the gradient. So it's kind of like it's kind of like a matrix times its transpose, and that's like why it's useful. So it's kind of like divergence of the gradient of a function. But in a sense, kind of like the divergence is kind of like minus the gradient, the transpose of the gradient. You know, again, like as I was saying, if you can take the transpose of a matrix, you can kind of take the transpose of the gradient, whatever that means. Like, I'm not going, right now it's not super important. But the reason why it's kind of like that's nice to see is because when you multiply a matrix that's its transpose, it always gives you a symmetric matrix, which has like, non-negative eigenvalues and this other stuff. So there's a lot of things that you get for free once you realize that you can write the Laplacian in that way. So, it's kind of like things that you kind of like learn along the way in more advanced courses. But again, like for now, you don't have to worry about it. The only reason that I'm bringing this up is to explain why I'm going to call this matrix the Laplace matrix. In fact, when we talk about graph theory, we'll talk about the graph Laplacian. Um, which is an important thing that is used in graph theory. And again, it is all called the Laplacian because of this like relation to the like the usual Laplacian of functions. That if you ever take partial differential equations, you will talk about that a lot because that's one of the big equations that you have to solve in PDEs. If you ever have to solve like again like if you ever take a course in electricity and magnetism, you have to solve like the Laplace equation in many different circumstances. So that was just kind of like a detour to explain the name of what I'm going to to define. So you can define the Laplace matrix. Now define or the Laplacian matrix. So it's just going to be this matrix. So I'll call it L. And I'll make a diagram in a moment just so that you see that it kind of like makes sense. But this is the most, in a sense, it's going to be the most important matrix in the entire course, basically. So we will use it over and over and over and over, like multiple situations. So just to make sure, like that kind of like the definition makes sense, like to go back to the diagram that I had, I had. Where do I have it? Oh, here you are. So I had the matrix B. I had the matrix A going this way. And if you remember what I had told you is that the way to think about the transpose is that it is a matrix that runs in the opposite direction because the transpose switches the sizes of the matrix, right? So it goes the opposite way. So the matrix A transpose goes this way, and the matrix B transpose goes this way, right? So the transpose, like the point is that it reverses the direction of the matrices. So if you start, right, if you start with the vector u, if you start with the vector u, kind of like the way to think about it is that, oh, you want to take this vector on a right. I mean, and so you have to, so one way to take up this vector on a right is that you can hit it with A. If you hit it with A, you get A times U, and then you want to go back to where you started so that you return to where you were, kind of like a closed circuit. So you can hit this vector with A, that gives you A times U. And then to go back to where you started, right? To go back to where you started, in a sense, like back to the space where you were located, you can hit it with the matrix A transpose, right? So that's what corresponds to this main part A transpose A. And let me see actually if I can draw that here. Let me make this a little bit bigger. Right, so you can hit it with A transpose A. Let me put the so this is like this will give you A transpose of A times U. Okay, so again, you start with U, you go to the other side with A, and then you go back with A transpose. And then, but you could also have done the same with B. So if you have U here, you can go with B to, sorry. Now you have to start with the transpose first, right? Because B is going this way. So if you start with U, you can hit it with B transpose, then lands you on the other side. So this one is B transpose U. And once you're there, right? Once you're there, if you want to go back to where you were, right? If you want to go back to the state you were in, you hit it with B, and when you do B of that, like it would land somewhere in here. So let me put you in the middle. Let me put here you in the middle. So you hit this one with B, so you get B of B transpose U. B of B transpose U. Okay. And so basically the Laplacian, this Laplace matrix just takes into the account the two different ways that you can kind of like go back and forth and adds them together. So that's what the Laplacian is doing. Just adds both of those matrices together. Yes.
So is this for any A and B or for our specific?
Well,
I guess.
no, right. In a sense, like, if you had two matrices A and B, as long as they kind of like, have the correct sizes, you could always define this combination. Is that this ends up being most useful when you also have the condition that A times B equals 0, right? But yeah, this definition obviously does make sense even if A times B is not the zero matrix, but it's only in that case when there are these extra properties that will be useful. In fact, why well, actually, let me break it into two parts because it's useful to kind of just know what is true even before you use the information that A times B equals 0. So what can you say about this matrix before using that A times B equals 0? Uh, so what can you say about this matrix L, before using that A times B equals to 0? Okay. So again, like just to give you the formula for L was A transpose A plus B transpose, right? So what is completely true in general is that this is a symmetric matrix, So the first thing that you can say for sure is that this is symmetric. meaning that L equals L transpose. And implicitly that means that it's a square matrix, so maybe I should put that as property zero, right? So it is square, it's a square matrix, so this is loss zero, so it's a square matrix. That is kind of like easy to check, just based on how it was defined. If you just run down the formula, because it starts on Rn and ends on Rn, so it has to be n by n. But it's also symmetric. Why is it symmetric? Just to go quickly over this, what would be the transpose? Do you remember the transpose of a matrix? When it's a sum, you can just take individual transposes, right? And if you remember the transpose of a product, it's a product of the transpose flipped, right? So you can transpose, you can like do something like this. Right, so here what I'm using is that I'll use two different letters so that it's not too confusing. The CD transpose is D transpose times C transpose, right? So you flip the factors, and you flip the factors and you transpose each, right? So let's say if I did it correct. Flip the factors, so A goes to the first factor transpose, A transpose, transpose, okay? And then, right, B transpose gets transpose, and then B gets transpose. And then you just use an A transpose, A transpose, transpose is A, and then B transpose, transpose is B. So that gives you A transpose A plus B transpose. So those are two important properties, that is square and that is symmetric. And maybe even so far so good. This is also a positive semi-definite matrix. So if you have ever seen the gram matrix, when they talk about kernel methods, like it is similar to this gram matrix. So what that means, being positive semi-definite, one way to say that, there are different characterizations, but all its eigenvalues are non-negative. So any metrics, once it's symmetric from linear algebra, you know that all these eigenvalues are real. None of them are complex. That's what the spectral theorem says. So because L is symmetric, the eigenvalues are real. But what is true, moreover, because of this particular form of the matrix, moreover, you can say that they're not negative, because given this particular form of the matrix, the eigenvalues are non-negative. Okay. That's an important property to have, because, for example, once you have non-negative eigenvalues, you can just take their square root, and they're like real numbers, and you don't have to worry about complex numbers at all. So the proof that they are non-negative is kind of like fun enough to, it's like a nice exercise. So I mean, let's do it together because it doesn't take too much time to do, and it's like a fun thing to try. So what was an eigenvalue and an eigenvector for a matrix? It was a vector for which the matrix times that vector gives you lambda times the vector, right? So you would have that L, the matrix L times U is lambda times U, right? That was the eigenvalue, eigenvector equation. And then what I will do, let's see. So what I can do, I will uh let's see if if this is going to be a straightforward thing or not. Oh, let's go with it. We'll see, like if it's uh I'll try, because now I'm not so sure if this will be super easy to see, but I'll take dot product on both sides with L. Sorry, not with L, with U. Sorry, I meant take dot product both sides with U. Okay? So, okay, let's see. So what happens here? The dot product of a vector with itself is just the length of the vector squared, right? And then let's just use the particular form for this matrix. Let's see. Oh yeah, I think it will be fine. Like I was just worried for a moment, but I still think like the proof is a simple one. What is this formula for the matrix? The matrix was, where do I have it? Oh, I have it you there. A transpose A plus B transpose, sorry, B transpose U. Okay, so let me copy paste this one and we can continue it on the next page. Okay, and then you can, before doing the dot product, just like distribute this. So you're doing U dot A transpose A U plus B transpose U. But okay, so far so good. Okay, that maybe there's something weird. And then the dot product is distributive, right? So you can do U dot A transpose A of U plus U dot V transpose of U, right? And that's A lambda times the length of U squared. So far so good. Okay, but now this is where it's useful to have the definition of the transpose, the fancy definition of the transpose. So what was the fancy definition of the transpose? That you are allowed to move the matrix to the other factor provided you transpose it. That's the fancy definition of the transpose. So this matrix can be moved to the first factor if you transpose it. So let's now I'm going to use fancy definition of transpose. Okay, so the first I can move this A transpose to the other side by transposing it. So I'll put A transpose transpose. I'll put A transpose transpose U. And now I'm just left with an AU in the second factor, right? And then I can move this B. If you move the B, the price to pay is that you transpose it. So you transpose the B. So this is a super useful trick. Again, if you ever do like Carnot methods or least squares, like there are many places where this trick is used. So what like the first one, like the second term is a little bit more transparent maybe because that is a dot product of V transpose U with V transpose U, right? So that is just a dot product of a vector with itself. So it's the length square of that vector. So that the vector happens to be V transpose U. So this one is just the length of V transpose U squared. Because again, that's also important to remember. The dot product of a vector with itself is just its length squared. Okay, so this is just the dot product of a vector with itself is its length squared. And A transpose is A. So that's also A trans AU dot AU. So it's the length of AU squared. Oh, actually, oh my god, this is So good because I think it's going to help me to show like the thing that I actually wanted to show, but with, no, I don't know if I can. So what is he saying? This is saying, an eigenvector never has like a zero length, so you can divide both sides of the equation by length of u squared. So that gives you a formula for lambda, which is a completely useless formula, but it does tell you something about the sign of lambda, right? When that tells you the lambda, if you divide by the length of u squared. Oh, but what is happening? The denominator becomes negative, and this is a sum of squares, it's also negative, positive, right? Positive, but, or, I guess potentially it could be zero, that's fine, but it's not, neither of them is negative. So this guarantees that lambda is greater or equal to zero. Well, again, just to make a remark, this is kind of like a similar proof, when you talk about the Gram matrix, like, and this is similar to when you prove the Gram matrix, again, that's used in numerical analysis and so like machine learning, that the Gram matrix has, mm, it's non-negative, it's positive. Oh my God. So it's basically, in fact, a bit, more, this proof is a little more tedious because this matrix was defined as a sum of two things. Oh, so this matrix is already, okay, it's an interesting matrix because it's symmetric, has non-negative eigenvalues, okay? How is it connected? Uh, how is it connected to what we were talking about? So what we were talking about, sorry, just to go back for a second, where are you? Oh, so what we were talking about is that I was telling you, oh, these equivalence classes, a vector here in this intersection represents an equivalence class, like of this equivalence relation that I had defined. So kind of what you can show with, I'm going to just do half of the proof because it's kind of like very similar to, like, once you understand this half, like the other half would be, it's more or less the same. But this intersection can be written as the null space of this Laplace matrix. So instead of trying to figure out how to understand the null space of, like, sorry, instead of trying to think about the intersection of two subspaces, you can replace that with a single space, which is the null space of the Laplace matrix. So my main claim is that and that one will require that A times B equals the zero matrix. So here's the main claim for today. And once we have that in place, like next time we can start using this for like applications. So basically what I'll tell you next time is that like a generalization of a graph, which is kind of called like a simplicial complex. I'll start kind of like slow. I'll do it in 2 dimensions. But once you have that, you can kind of like define these matrices, and then you can compute the Laplace matrix, and then you can find the dimension of the null space of the Laplace matrix, and that kind of tells you the number of holes of the space. That's kind of what will happen. And which is kind of like a long story and kind of weird that you would use the like null spaces for that, but it's kind of like what makes it an interesting thing. And again, this uses that A times B equals zero, the zero matrix. So my main claim is that the intersection sorry, I think about this with kernel, null space. That the null space of A intersected with the null space of the transpose is just the null space of this Laplace matrix. So the null space of the Laplace matrix will be the most concrete way of thinking of these equivalence classes. So kind of like the null space. Again, here, just remember that L was A transpose A plus B transpose. Okay. So how do you prove the equality? Again, these are vector subspaces, but they're sets. So what is the most convenient way of proving an equality between sets? And what you do is that you prove that every element in this set is in this set, and that every element in this other set is in the other. So kind of like both inclusions. So kind of like the easiest one is to just, again, neither is too long. I think I should have enough time to do them quickly. Why is the null space of A intersected the null space of B inside the null space of L? Well, again, what does it mean to be in the null space of A? That means that A times U equals 0. What does it mean to be in the null space of B transpose? That means that B transpose times U equals 0, right? So if you have a vector that is in the intersection, it's a vector for which A times U is 0 and for which B transpose U is 0. That's what it means to be in both null spaces. So and then in that case, what is L times U? Well, L times U is the same as A transpose A plus B transpose times U, right? And then you use the distributive property, and that's just like A transpose A U plus B transpose U, right? And you could, okay, A U is 0 because you're in the null space of A, and B transpose U is 0 because you're in the null space of B transpose. So like these automatically 0. Okay, so that one is an easy. You see, so as I was saying, this one is not the hard one. Sorry. So that is why the null space of L, contains the null space of A intersected with the null space of B transpose. And there I'm not using that A times B equals 0. So A times B equals 0 will be used for the other inclusion. Okay, so let me see if I can answer it here. So why is the null space of L inside the intersection of the null space of A with the null space of B transpose? And this is where I'm going to use that A times B equals 0. So again, what does it mean if someone is in the null space of L? That means that L times U equals 0. But what is L? L is A transpose A plus B transpose. Right? So if you, again, you can distribute because matrix multiplication with the sum, distribute, and let's just move one of the factors to the other side. So if you do this, you get that A transpose A times U is minus B transpose U. Okay, right, so you just distribute and just move the second factor to the other side. Okay, but then, okay, then when you get to this point, I multiply by A both sides of the equation. Okay, I'm going to multiply by A both sides of the equation. Huh, but A times B equals 0. So that is finally where that's being used. So if A times B equals 0, what you end up getting, what do you end up getting? You just end up getting that A times A transpose times A times U equals 0, which looks like it's still kind of like a bit long. But what that's saying, another way of saying this is that A transpose A U is in the null space of A. Okay. Sorry. Let me, okay, let me, I'm almost done. Again, I just want to give you the ideas like of these proofs because they're kind of like tricks that are useful to keep around if you ever take a more like an advanced math class. So, that means that A times this vector equals 0. So A times this vector equals 0. So A transpose A U is in the null space of A. Oh, actually, like, let me do it in a. Do I want to do it this way? No, because I have three things. Okay, but then, but also, and it looks kind of silly, but also, and I should almost be wrapping this up. But A transpose A of U is A transpose of A U, which kind of like seems dumb, right? But so it is for A transpose of something. So what that means is that A transpose AU is in the image of A transpose. Okay, so or in the column space. If you call this, what should I call this? W. So this would be A transpose W. And those are precisely the vectors that you can write in. Those are the vectors that are in the column space of something. So it's in, yeah, this part is a bit, I mean, just, you know, it's a little bit more technical, but I'm just writing it for completeness. So, but the column space of A transpose, because of, like this orthogonal complements and rank nullity theorem and all this other stuff. That's just the null space of A. So this is the rank nullity stuff. Okay. And so that means that A transpose this is, yeah, Where am I? So here I'm going in circles, I think. Give me 1 second, if not, I'll finish for today and I'll kind of finish like next time. Or I'll just fix it in the notes because it's like a little bit tedious. And it may be better just to have it written down and then you can kind of see it again because let's see, I'm doing here. What am I calling? French. And. Oh, I see. Yeah, no, like it's fine, but yeah, I'll complete it in the notes because it's like a bit too tedious to kind of like go over it in class. I'll put it there so that if someone wants to read it, like they can read it. But you know, it's almost there. But yeah, it still will take some time. The important thing to summarize is that these two null space, like this null space, is an intersection of these other two. So whenever we want work with the equivalence classes, we'll just focus on finding the null space for this matrix, and that's it. You know how to find null spaces from linear algebra, right? So it's just Gauss-Jordan, essentially. So we have reduced all this problem to Gauss-Jordan, basically. If you think about it, like, but kind of like the interesting thing is like, oh, that these matrices again represent information about whether your space has holes or not, or things of that sort. So, but now there is only linear algebra at this point. There's no more orthogonal complements. All this other stuff has been kind of like hidden in this null space. So that's why it's useful. Sorry, yes.
Obviously, working through the whole.
Mhm.
They took the O, the
Uh-huh.
whole definition. Because the
Oh.
Y component exists once.
Oh, well, let's finish here. Let me, and we can, if you can, if you want, I'll just, which one is that one? Oh, right, you're right. I'll fix it. Thank you. Oh, right, we're even assume, if you want, you can assume that they're, yeah. Yeah, I mean, probably you only need to take one derivative, right? So like.
Point two for this volume.
Oh, right, for that one, for those, yes, yeah. But yeah, I'm kind of like not worrying too much about the, like the. Make them as smooth as you need, but yeah, like if you, it's easier. The reason, wait, let me just pause the recording, because you're taking more advanced math classes, right? Yeah, okay, so I can tell you more of the reasons for why.
This is suspicious. This is not always true.
Yeah. So. So what happens, like, if you look at the, yeah, the thing is like, I didn't want to